Welcome to Astronomy Daily, your go-to podcast for all things space and astronomy news. I'm Anna.
And I'm Avery. We're so glad you're joining us today for another exciting dive into the cosmos.
Today, we'll be talking about a new record in detecting incredibly distant signals from the early universe.
Plus, we'll check in on a fascinating planetary mission that just completed a crucial test near Mars, giving us a sneak peek at its capabilities. And get ready to hear about a mysterious visitor from beyond our solar system, captured for the first time by none other than the Hubble Space Telescope. To top it all off, we'll give you a rundown of a very busy week ahead in space launches, featuring everything from Vulcan and Ariane 6 to multiple Starlink missions. Let's get started.
All right, let's kick things off with a truly groundbreaking discovery that's pushing the boundaries of our understanding of the early universe. Astronomers have traced a fast radio burst, or FRB, to a record-breaking distance across the cosmos. This new FRB, designated FRB 2024-0304b, was initially detected on March 4, 2024, by the Meerkat Radio Telescope Array in South Africa. But what makes this one so special is its incredible distance.
That's right. It has a redshift of 2.148, which means we're looking at light that traveled for over 11 billion years to reach Earth. To put that in perspective, this burst originated just 3 billion years after the Big Bang, pushing our observational boundary of FRBs much further back into cosmic time. Previous detections only reached about halfway through cosmic history.
That's right. Finding the exact source of this signal was a real piece of detective work. Initially, ground-based observatories and archival data couldn't pinpoint its host galaxy. But a follow-up with the James Webb Space Telescope's NIRCam and NIRSPEC instruments did the trick, revealing the FRB's host galaxy and getting a spectroscopic redshift. The burst's radio waves dispersed at a rate of about 2,330 parsecs per cubic centimeter, acting like a cosmic fingerprint that confirmed its extremely distant origin. This measurement tells us how much the signal was stretched and delayed by free electrons as it journeyed through space. The host galaxy itself is quite revealing. It's described as a low-mass, clumpy galaxy that's still relatively young and actively forming stars. The presence of an FRB in such a galaxy strongly supports the theory that these mysterious bursts originate from young magnetars, which are highly magnetized neutron stars. This suggests an origin that can occur over relatively short timescales, rather than processes that take billions of years to develop.
This discovery effectively doubles the redshift reach of localized FRBs, allowing us to probe ionized baryons across about 80% of the universe's history. It also establishes FRB activity during what astronomers call cosmic noon, which was the peak period of star formation in the universe's history.
It's fascinating how these millisecond-long bursts can encode so much information about the plasma permeating our universe, giving us insights into magnetic fields and gas distributions. The observations also reveal complex magnetic field structures spanning gigaparsec scales along the burst's sightline, as it passed through various cosmic structures.
As next-generation telescopes come online, discoveries like FRB 2024-0304b are truly exciting. They show us how these fleeting signals can act as messengers from the universe's distant past, helping us piece together how it evolved from its chaotic youth into the structured cosmos we see today. It's just incredible.
From exploring the distant past with FRBs, let's now turn our attention to an upcoming mission that's preparing to unlock the secrets of one of Jupiter's most intriguing moons. NASA's Europa Clipper Mission, which began its long journey to Europa on October 14, 2024, recently had a crucial pit stop. On March 1st, the probe reached Mars, not just for a gravity assist maneuver, but also to perform a vital test. While orbiting the red planet, mission controllers on Earth seized the opportunity to test the probe's REASON instrument. REASON stands for Radar for Europa Assessment and Sounding, Ocean to Near Surface.
This radar instrument is absolutely critical for the mission's primary goal to probe beneath Europa's icy sheet and search for pockets of water that could potentially harbor life. It's also designed to give scientists a glimpse of Europa's interior ocean and shed light on how material might be transferred from the interior to the surface.
The test was a complete success, producing a radargram that showed the outline of Mars's topography. This gave the team a fantastic preview of what the probe will see when it arrives at Europa. Reason relies on two pairs of antennas that extend from the spacecraft's massive solar arrays, measuring an impressive 17.6 meters from tip to tip.
Testing this instrument in space was crucial because certain aspects, like the echo test, where the radar signals bounce back, simply couldn't be performed on Earth once the actual hardware was built. Dom Blankenship, the principal investigator for the radar instrument, said, "We got everything out of the flyby that we dreamed. The goal was to determine the radar's readiness for the Europa mission, and it worked. Every part of the instrument proved itself to do exactly what we intended."
During the test, Reason sent and received radio waves for about 40 minutes, while the spacecraft flew about 5,000 kilometers above Mars's surface, gradually lowering to 884 kilometers. For comparison, once it's at Europa, Reason will operate when the Clipper is as close as 25 kilometers to the moon's surface.
The instrument team collected a staggering 60 gigabytes of rich data, which they started transmitting back to Earth in mid-May. Scientists have been poring over this data, and it has confirmed that Reason is in perfect working order. Trina Ray, Europa Clipper's deputy science manager, shared the excitement, saying that all of us who had worked so hard to make this test happen, and the scientists seeing the data for the first time, were ecstatic, saying, "Oh, look at this! Oh, look at that!"
This Martian test has given the science team a head start on learning how to process the data and understand the instrument's behavior, exercising those muscles just like they will out at Europa. The Europa Clipper's total journey to the icy moon will be about 2.9 billion kilometers, and it includes one more gravity assist using Earth in 2026. Currently, the spacecraft is about 450 million kilometers from Earth, steadily making its way to Jupiter.
That's an incredible level of preparation for the Europa Clipper. Speaking of unique opportunities to study distant objects, let's pivot to something truly rare, an interstellar visitor to our solar system.
Astronomers using the Hubble Space Telescope have captured stunning observations of 3I/Atlas for the first time. This is only the third confirmed object from outside our solar system ever known to visit our cosmic neighborhood, following Oumuamua in 2017 and Borisov in 2019. Each of these objects offers a unique window into planetary systems around other stars.
What makes 3I Atlas particularly fascinating is its behavior. Even at 3.8 astronomical units from the Sun, almost 4 times farther than Earth is from the Sun, it's already showing significant activity. Unlike asteroids, which typically remain largely unchanged, 3I Atlas is behaving more like a comet.
That's right. As solar radiation heats its surface, the object is releasing streams of dust particles, forming a distinctive tail pointing away from the sun. This comet-like activity provides astronomers with a rare opportunity to study material that originated in an entirely different star system.
Using exceptional resolution, the research team, led by David Jewett from UCLA, was able to have its first close look and estimate how much material 3I Atlas. They calculated the mass loss rate in dust to be between 6 to 60 kilograms per second. To put that into perspective, that's roughly equivalent to losing the mass of a small car every few minutes, which is a significant amount for such a distant and relatively small object.
The team also worked to determine the size of 3I ATLS's nucleus, though this was challenging since they could only see the glowing cloud of dust, not the solid core directly. By analyzing the brightness distribution of the surrounding coma, they estimated the nucleus has an effective radius of less than 2.8 kilometers, assuming it reflects only about 4% of the light that hits it, similar to charcoal.
This size constraint is crucial for understanding its composition and history. For instance, if its activity is driven by carbon monoxide turning from solid to gas, the nucleus cannot be smaller than 0.16 kilometers in radius. Different materials require different amounts of solar heating to begin sublimating, so observing how and when 3I ATLS becomes active helps scientists make educated guesses about what it's made of.
These first Hubble observations of 3I/Atlas represent a significant step forward in our ability to study these cosmic messengers. They offer insights not only into the object itself, but also into the distant stellar system that sent it on its incredible journey through the galaxy. It's like getting a postcard from another star system, carrying chemical signatures and physical characteristics shaped by alien environments billions of kilometers away. From ancient light to interstellar visitors, we've covered some truly mind bending topics today. But let's shift gears and look at the more immediate future, because it's shaping up to be a very busy week for launches.
You're not kidding, Anna. We've got a packed schedule coming up with several significant missions. First up, ULA's Vulcan rocket is scheduled for its first launch of 2025 on Tuesday, August 12th. This mission, designated USF-106, will carry a Technology Demonstration Navigation Satellite, NTS-3, and a classified payload for the U.S. Space Force into geosynchronous orbit.
And just a day later, on Wednesday, August 13th, Europe's newest launch system, the Ariane 6, will have its second flight of 2025. This mission will carry the METOP-SGA-1 weather satellite for EUMETSAT, which is crucial for monitoring weather, climate, and the environment from space. It even includes the Sentinel-5 instrument for global air quality monitoring.
On the same day, a Chinese Tianzhang 5B rocket is expected to launch carrying a batch of communication satellites, likely part of China's ambitious SatNet constellation. Beyond these, we also have 4 SpaceX Falcon 9 Starlink missions planned throughout the week, deploying hundreds of internet satellites into orbit. It's an exciting time to be watching the skies.
What a week it's shaping up to be for space enthusiasts. From record breaking distance signals to critical tests for our missions to the outer solar system, and even a visit from another star system, it's been a truly captivating episode.
Absolutely, Anna. And let's not forget that jam-packed launch schedule coming up with new rockets and dozens of satellites heading to orbit. It just goes to show how dynamic and exciting the world of astronomy and space exploration truly is.
We hope you enjoyed diving into these fascinating stories with us. Thank you for tuning in to Astronomy Daily. And remember to visit our website at astronomydaily.io for even more from the Astronomy Daily team.
Keep looking up, stay curious, and we'll catch you tomorrow for more news from across the cosmos.